Very well. We are on to the second lecture of Unit 1, and that is graphite and fullerenes. Of course, many of us are very familiar with these words. So, let us take up a little detailing of it as per our syllabus. In this particular topic, we will be studying Introduction to Graphite, Structure of Graphite, Properties and Applications of Graphite, and thereon we will be taking up fullerenes, structure of fullerene, preparation, properties and applications of fullerene. First of all, let us begin with graphite. So, what is graphite, and let us talk a little about its structure as well. So, graphite basically is of course a form of carbon, an allotrope of carbon. Okay. So, in graphite the carbon atoms are joined together and arranged in layers. The links between the carbon atoms in the layer are very strong, but the force of attraction between the two layers is not that very strong. The two layers are held together by weak van der Waals forces. The layers easily therefore slip over each other because van der Waals forces are weak, and the interlayer distance is a little much high compared to the bond length, of course. So, they can easily slip over each other by application of force. So, that is why graphite is used in pencil leads, because it is soft and slippery. So, when it is dragged onto a paper, it leaves impression on paper, and that is how we can write. So, graphite of course we know is a non-metal. Why? Because it is made of carbon, that is why it is non-metal. And it is the only non-metal that of course conducts electricity. So, let us have a look at the structure of graphite. Important is the structure of graphite. At times questions are asked based on structure as well. So, each carbon in graphite is bonded to 3 other carbon atoms, making use of 3 sp2 hybrid orbitals. So, let us have a look at each carbon. This is a carbon. This is a carbon. Now, this particular carbon, normally we know that carbon has sp3 hybridization. So, each carbon over here is using 3 sp2 hybrid orbitals. What about the third p orbital? The third p orbital remains unhybridized and lies perpendicular to the plane of the molecule. So, the unhybridized p orbital it lies perpendicular to the plane of the molecule in case of graphite. Now, these unhybridized orbitals often merge with each other and they appear like a big huge pi bond, and that is why the carbon-carbon bond in graphite is about 1.42 angstrom, as mentioned over here, 0.14 nanometers. Now, we all know that carbon-carbon double bond is about 1.22, carbon-carbon single bond is about 1.54, and this is in between the single and the double bond because of this huge gigantic pi bond like structure which develops with the help of unhybridized p orbitals. The p orbital which remains unhybridized and is perpendicular to the plane of the molecule, they undergo merger. Now, this carbon-carbon bond in case of graphite has some sigma bond character and some pi bond character. It has 2/3 sigma bond character and 1/3 pi bond character. This also must be taken into consideration. Okay. Now, The interplanar distance, the distance between the two planes, is 0.34 nanometers, which is much higher than the bond length of carbon-carbon in case of graphite. And the two sheets are held together by weak van der Waals forces, therefore they can slip over each other, and that is the reason why graphite is a good lubricant. So a question is asked, a 2-mark question, why is graphite a good lubricant? So you can explain it in this way: the interplanar distance is much higher than the bond length. They are held, the two sheets are held together by weak van der Waals forces, and therefore they slip over each other on application of force, and hence graphite is a good solid lubricant. Another question: why is graphite a good conductor even though it is a non-metal? Now, because of a lone electron in these p orbitals, because of a lone electron, this electron does not undergo bond formation, it lies as it is, and it is delocalized throughout the material. Therefore, when you apply electric current across a sheet, these electrons easily mobilize and facilitate in conduction of electricity. Okay? So, we have already discussed much about the structure. Graphite has a planar 2-dimensional hexagonal sheet like structure, where each carbon is directly and covalently bonded to 3 other carbon atoms, making use of 3 sp2 hybrid orbitals. Okay? The unhybridized p orbital having a single electron lies perpendicular to the plane of the molecule, and such p orbitals undergo overlap as we have discussed, okay, and form a merged huge pi orbital structure. Delocalized electrons are present in it, and therefore it shows good conduction of electricity. Let us talk of the properties of graphite. It has high melting point. The reason is because of a large number of covalent bonds. Then the density of graphite is 2.25 grams per centimeter cube. It is of course lesser than that of diamond. Diamond has a density of 3.5 or 48 to be precise grams per centimeter cube. Low coefficient of friction, because we can see it in the diagram. We can see it in the diagram because, see, they are held together by weak van der Waals forces, and there are no irregular structure. So, the coefficient of friction is going to be low, and that is what makes it a good lubricant. Okay. Good conductor of electricity, as I had told you, it has a lone electron in unhybridized p orbital which easily mobilizes, and therefore conduction of electricity is facilitated. It is soft and flaky, and because of this reason, soft and flaky, again it is used in pencil leads, and black and shiny, having a metallic luster. So, when it is rubbed across, when it is stretched across, scratched across a piece of paper, it leaves that kind of an impression. Because of that, we can use pencil leads to write on paper. And graphite absorbs neutrons, and that is why graphite rods are used as control rods in nuclear reactors, and that is a very good application of graphite. Now, let us talk of the applications of graphite. It absorbs it is used for making electrodes. Why? Because it conducts electricity. Used as solid lubricant, we have been talking of it. Used in pencil leads, we have also discussed this very well. Used for preparation of fullerenes. Now, the next topic we are going to study fullerene. When we study preparation of fullerene, one of the starting material, the precursor, is going to be graphite. Used for making, and graphene layers are used for making nanotubes as well. Okay, used for making synthetic diamonds as well, and used as control rods in nuclear reactors for preparation of nanomaterials, the single wall and the multi-walled carbon nanotubes. So, let us move on to fullerenes. What are fullerenes? And we will discuss a lot about fullerenes now. See, basically the word fullerene, how did it come? Way back in some times like late 1970s and 1980s, जो 80 का दशक था पिछली शताब्दी का, वहाँ पर उस समय जो 70 का दशक था, वहाँ पर अमेरिका में बहुत सारी बिल्डिंग्स ऐसी बनाई गई जो सर्कुलर डिस्क लाइक स्ट्रक्चर थी, और उनके डिज़ाइनर थे बकमिंस्टर फ्यूलर, वो एक आर्किटेक्ट थे। अब इसी एरा में, इसी ड्यूरेशन में फुलरीन की खोज हो चुकी थी, फुलरीन पर बहुत सारी स्टडीज़ हो रही थी। अब जैसे कि अगर आपको याद हो, बेंजीन का जब स्ट्रक्चर सोचा गया तो क्या था, केक्यूले ने अपने ड्रीम में एक सांप को इंटैंगल किया हुआ, मुड़ा हुआ पाया, और बेंजीन के स्ट्रक्चर के बारे में उन्हें आइडिया आया। इधर क्या हुआ, फुलरीन की खोज हो चुकी थी, लेकिन इसका स्ट्रक्चर बनाना एक बड़ा टारगेट था हमारे सामने। तो उस समय बकमिंस्टर फ्यूलर साहब ने कुछ बिल्डिंग्स ऐसी बनाई थी जिसमें 60 कोने होते थे, 32 फेसेस होते थे, जो पेंटागन और हेक्सागन के कॉम्बिनेशन से बनी हुई बिल्डिंग्स थी। उन बिल्डिंग्स को देख करके साइंटिस्ट लोगों को भी आइडिया आया कि क्या हम फुलरीन के स्ट्रक्चर को इसके आधार पर रख सकते हैं और उसको फिर QED हेंस प्रूफ भी कर सकते हैं। इस तरह से फुलरीन का स्ट्रक्चर बनाया गया। अब क्योंकि बकमिंस्टर फ्यूलर साहब के जो बिल्डिंग्स थे उनसे आइडिया लिया गया, तो फ्यूलर साहब को इज्जत बख्शी गई, उनको ऑनर किया गया, एंड दिस मॉलिक्यूल वाज नेम्ड एज फुलरीन in the honor of Buckminster Fuller, who was an architect and not a scientist. Okay, so fullerene is a polymorphic form of pure carbon. This again is a pure carbon, but why do we call it polymorph? Because once the units become more than 20, we don't call it oligo, we call it poly. So जैसे polymer होते हैं, उसीलिए हमने polymorphic form of carbon इसको बोला है. The most popular fullerene has 60 carbons in it, which has a icosahedron structure with 60 vertices, 32 faces, 12 pentagonal and 20 hexagonal. Each vertex has a carbon which is linked to two other by two single and a double bond. The molecule is aromatic, showing several resonating structures. The structure of fullerene resembles that of a buckyball or a soccer ball. जैसी कि सॉकर की गेंद होती है, उसकी तरह इसका स्ट्रक्चर होता है. Let's talk of the structure of fullerene. So fullerene shows a normal face-centered cubic lattice indicating the solid to be acting like a liquid. The molecule tumbles on its lattice side. That means at a point of time it may appear to be like a tumbling molecule, like liquid crystals tumble. Okay, but it is of course not a liquid crystal. This has been proved with the help of X-ray crystallography and nuclear magnetic resonance studies. Drawing the structure of fullerene is a target in itself. वो एक अपने आप में important issue है, कैसे बनाया जाता है. सबसे पहले हम एक पेंटागन बनाते हैं. इस पेंटागन के पांचों आर्म्स पर हम हेक्सागन ड्रॉ करते हैं. इस प्रकार से उसके बाद जहाँ जहाँ ये हमें कुछ हेक्सागन के छोटे छोटे वैलीज जैसे नज़र आते हैं, ओके, उस जगह पर हम इस तरह से लाइंस ड्रॉ करके और फिर इसे हम एक गोलाकार आकृति दे देते हैं. इस प्रकार हम बहुत ही आसानी से फुलरीन का स्ट्रक्चर बना सकते हैं. तो ये बन गया हमारा फुलरीन का स्ट्रक्चर. ठीक है, तो फुलरीन का स्ट्रक्चर बच्चों को थोड़ा सा डिफिकल्ट लगता है ड्रॉ करने में. उसको क्या करना है, हमें पहले एक पेंटागन बनाना है. पेंटागन की 5 आर्म्स पर हमें 5 हेक्सागन्स बनाने हैं. उसके बाद हेक्सागन्स के जो ये एक वैली लाइक स्ट्रक्चर्स आएंगे, उनको हमें जो थोड़ा सा स्ट्रेच आउट करके उसके चारों तरफ एक गोला बना देना है. ये बन गया फुलरीन का स्ट्रक्चर. ठीक, अब इसमें आप देख सकते हैं कि 1 2 3 4 5 और 6 पेंटागन है. 6 आगे 6 पीछे, 12 पेंटागन हो गए. काउंट करिए, हेक्सागन 1 2 3 4 5 6 7 8 9 10 हेक्सागन हो गए, 10 आगे 10 पीछे, तो 20 हेक्सागन हो गए। ये बन गया फुलरीन का स्ट्रक्चर। अब हम बात कर लेते हैं फुलरीन को प्रिपेयर कैसे किया जाता है। इसकी कोई नॉर्मल लैब प्रिपरेशन नहीं होती है, थोड़ा डिफरेंट तरीके से इसको बनाया जाता है। क्या करते हैं, एक कार्बन का आर्क व्हेन स्ट्रक अंडर आर्गन एटमॉस्फेयर, आपको एटमॉस्फेयर न्यूट्रल चाहिए, बिकॉज अगर ऑक्सीजन होगी तो कार्बन को हीट करेंगे, वो जल करके कार्बन डाइऑक्साइड बन जाएगा। तो व्हेन अ कार्बन आर्क इज स्ट्रक अंडर आर्गन atmosphere at a low pressure 0.05 to 0.1 atmospheric pressure, a black soot like dusty material is obtained, and this black soot like dusty material contains fullerenes. So the soot is extracted with solvent like toluene, filtered, solvent evaporated, it has crude fullerene in it, then it is sublimed under vacuum at about 600 degrees Celsius. The sublimation product is taken, scratched out, and column chromatography की मदद से इसको प्योरीफाई कर लेते हैं। 4 से 15% फुलरीन हमें प्राप्त हो जाता है। एक और तरीका, बेंजीन ऑक्सीजन कंबशन फ्लेम in a carefully diluted argon atmosphere generates soot containing 4 to 15% of fullerenes. Purification is the same. Soot is taken, extracted with toluene, filtered, solvent evaporated. The resulting product is sublimed, okay, under vacuum at about 600 degrees Celsius, and the sublimation product को हम क्या करते हैं, उसको हम ले लेते हैं, निकाल लेते हैं, उसको फिर कॉलम क्रोमेटोग्राफी की मदद से फर्दर प्योरीफाई करते हैं। इस प्रकार हम फुलरीन की सिंथेसिस करते हैं। फुलरीन की सिंथेसिस के लिए हम ऑफ कोर्स 2 सिंथेसिस हमने यहाँ पर मेंशन कर दी हैं। इसके अलावा हम फुलरीन को एक और तरीके से भी बना सकते हैं। हम क्या करते हैं, ग्रेफाइट लेते हैं, उसको हम वेपराइज करते हैं हीलियम एटमॉस्फेयर में और लो प्रेशर और हाई टेम्परेचर पर, जैसा कि यहाँ पर मेंशन किया गया है। और उसके बाद हमें एक सूट मिलती है, उस सूट को हम इकट्ठा करते हैं, अगेन उसका सेम प्रोसेस करते हैं, हम सूट को एक्सट्रैक्ट करते हैं सॉल्वेंट की मदद से और फिल्टर करते हैं। फिल्टर करने के बाद सॉल्वेंट उड़ाते हैं, जो हमें मटेरियल मिलता है उसको हम सब्लाइम करते हैं, सब्लिमेशन प्रोडक्ट की कॉलम क्रोमेटोग्राफी करते हैं और उस प्रकार हमें 4 से 15% तक प्योर फुलरीन प्राप्त हो जाते हैं। Now let us look at the properties of fullerenes. What are the properties of fullerenes? फुलरीन एक बहुत ही इम्पॉर्टेंट मॉलिक्यूल है जो कि बहुत जगहों पर प्रयोग किया जाता है। इसका नैनो साइंस में भी बहुत अधिक इम्पॉर्टेंट है, क्योंकि फुलरीन इटसेल्फ इज़ अ नैनो पार्टिकल, दैट इज़ वाई। ओके, so let us have a look at some of the properties of fullerenes as mentioned over here. Fullerene will display aromatic properties because it follows Huckel's rule, and that is why, because see, each carbon is bonded by 2 single and a double bond, so it has quite benzene like structure in between, alternate single double bond following Huckel's rule, and therefore it will show aromaticity also. Okay, apart from that, Fullerene has a cage like structure. We had taken it up earlier. It has a cage like structure, okay, and this cage measures 7 to 15 angstrom units. So if it has a diameter 7 to 15 angstrom units, so that means it will be a nanomaterial. Why? Because nanomaterials are the ones which are in nano dimension, on nano scale, at least in 1 dimension. So 15 angstrom means 1.5 nanometers. Now it can be compressed. Fullerene molecule, we are discussing the properties. Fullerene molecule can be compressed to lose its volume, let us say by 30%. This is again giving it a ball bearing like structure, and that is why fullerene can be used as a very good solid lubricant too. Then it sublimes under vacuum. We've already discussed that it sublimes under vacuum at about 600 degrees Celsius. This is also one of the property of fullerene. Thermally stable and tough, and this cage of fullerene breaks above 1000 degrees Celsius. It doesn't break below that. Okay. Single fullerene is yellow in color. In bulk, this fullerene may appear black in color, but a single fullerene is yellow in color. Okay. Then normally fullerene dissolves in benzene, toluene, xylene, etc. And when fullerene dissolves, it shows magenta color. So these are some of the properties which are very important to be taken into consideration. You may note it down. It is highly electronegative and photosensitive in nature. Okay. Now, fullerene may polymerize under UV radiations. Two of the fullerene units may club together and form a dimer. And when it forms a dimer, it becomes insoluble in toluene because the molecule becomes a little larger. Therefore, it does not fit into the intermolecular spaces of the solvent. So, therefore, fullerene polymerizes under UV radiations. Okay. Then fullerene, one of the major property is that it exists as a discrete molecule. That means as a single molecule it is stable and it exists as a single molecule. So, what is important is that it has its existence as a single molecule also. Graphite does not exist as a single molecule, and so does the diamond does not exist, but fullerene does exist independently as a single molecule also. That is also important as a property. Okay. So, it can behave like a superconductor when mixed with certain impurities, and otherwise pure fullerene is more like an insulator. But when you add like dope into it, when you add impurities to it, it behaves like a superconductor as well. So, let us talk of some of the applications of fullerenes. Okay. So, let us talk of the applications of fullerenes. Now, fullerene is recently discovered, though it existed down the ages, but its discovery is recent. In 1970s it was majorly worked upon, and in 1982 the nomenclature was given to it. It was named as fullerene. Okay. A lot of studies were done about it, and the major applications, of course, it is used as a solid lubricant. Why? Because it exists as a discrete molecule and the fullerene molecules behave like very small nano ball bearings. So, you know how beautifully it can be used like a lubricant at a nano scale. You do not even require much of it. Then it is used as a superconductor when mixed with certain alkaline metals like potassium. It becomes a superconductor. It is used as a soft ferromagnet. It is used as a catalyst and catalyst supporter. Now, a beautiful example of fullerene as a catalyst. See, the cage of fullerene is able to absorb 48 hydrogen atoms on its surface. You can take a note of it. So, each fullerene molecule can absorb 48 hydrogen atom on its surface. So, 48 hydrogen atoms can be absorbed on the surface of a fullerene molecule. Okay? So, therefore, it can be a very good catalyst. If you remember Haber's process, in the Haber's process a nickel gauge, a gauge had to be taken on which hydrogen had to be absorbed, and a single fullerene molecule can absorb 48 hydrogen atoms. So, it is a very good catalyst and a catalyst supporter, used for the preparation of synthetic diamonds. We all know how expensive diamonds are. So, the synthetic diamonds of course are prepared using fullerene as a precursor. It brings down cost tremendously. It is used for plant growth regulation. Now, what do we mean by plant growth regulation? See, since fullerene is a nanoparticle, it has tremendous lot of, when in the next lesson when we are going to study nanomaterials, we will be taking care of how on nano scale the properties of materials change tremendously. That is why fullerene is used for plant growth regulation. It is used in electronic and microelectronic devices. Now, it's an era. Earlier it was an era of electronic devices, then became microelectronic devices. If you talk of the chip also that is used in your mobile phone, now you have the nano chip. In your computers also, now you have the nano chip. So, it's an era of nanosciences, it's an era of nanomaterials, and fullerene is beautifully used in electronic and microelectronic devices. It is used in non-linear optical devices. Now, I hope so many of you must be doing a lot of study and of literature, a lot of study of science, where you know how linear and non-linear optical devices are used and play a very important role in present day technology. Fullerene is used as a nanomaterial for making nanotubes. Now see, fullerene has, in one of the dimension is on nanoscale. If you have an elongated fullerene, that becomes nothing but a nanotube, a tube like structure which has nanoscale in one of the dimension, maybe the diameter is on nanoscale. So, they are used for preparation of nanotubes also. Okay. Now, used in pharmaceutical industry, fullerene is used in pharmaceutical industry as anti-AIDS drug. What do we mean by anti-AIDS drug? We know that a lot of chemotherapy goes on when carcinogenicity is formed and when acquired immune deficiency syndrome happens. So, fullerene finds an application there too in pharmaceutical industry to be used in anti-AIDS drug. In fact, on nanoscale, these fullerene units, the nanotubes, are beautifully being used to deliver a drug into the biosystem. Like you have a capsule. So, you have a capsule, you put medicine into it and then you eat it. Similarly, the fullerene nanotubes are being used, okay, for pharmaceutical applications as well. So, they find a lot of application in pharmacy too. Okay. So, therefore, for making carbon nanotubes, single wall, multi wall, we use fullerene in plenty. So, this was our lesson regarding graphite and fullerene. Both have been derived from carbon. One of course is an allotrope of carbon, graphite, and fullerene is a polymorphic form of carbon. Both these appear in our syllabus. Questions are asked based on it, but fullerene is a contemporary molecule being widely used in industry, technology, etc. So, thank you for attending this particular class. I hope you had a good learning and I hope you will be preparing for your exams accordingly. Thank you. This is your teacher, Dr. Manisha Shukla, signing off from this class. Thank you.